Hey, what's up, Chem peeps? Let's take a look now at the Bronsted Lowry definition of acids and bases. In these two examples, we are asked to identify the Bronsted Lowry acid, the Bronsted Lowry base, the conjugate acid, and the conjugate base in each of the equations. Okay, before we start, let's recall that a Bronsted Lowry acid is a proton or hydrogen ion donor, and that a Bronsted Lowry base is a proton or a hydrogen ion acceptor. So let's start with the very first thing we come across in this first equation, HCl. To identify this as a Bronsted Lowry acid or Bronsted Lowry base, let's look at what HCl becomes on the product side. It becomes Cl minus. In order for HCl to become Cl minus, must it have donated or accepted a hydrogen ion? Answer, donated, which makes HCl a Bronsted Lowry acid and Cl minus its conjugate base, or what remains after the acid donates its hydrogen ion. Now, we can always identify two acid-base conjugate pairs in a reaction. Let's look now at ammonia, NH3, and think about what it becomes on the product side. Ammonium ion, NH4+. In order for NH3 to become NH4+, must it have donated a hydrogen ion or accepted a hydrogen ion? In this case, it accepted a hydrogen ion, making this a base and the ammonium ion conjugate acid. So, one more time, HCl becomes Cl minus, and it does so by giving up a hydrogen ion. By definition, that makes HCl an acid and the chloride ion its conjugate base. NH3 is going to accept a hydrogen ion and become NH4+, making NH3 the base and NH4+ its conjugate acid. Now, this is an equilibrium situation indicated by the double-headed arrows. If this reaction were to go in reverse, notice that NH4+, which we've designated an acid, would in fact act like an acid in the reverse direction. It would donate its hydrogen ion in order to return to the form NH3. And the chloride ion, which we designated a conjugate base, would in fact act as a base and accept a hydrogen ion to reform HCl. All right, let's take a look at the second example. We're starting with the hydrogen carbonate ion, HCO3-. Let's think about what it turns into. It turns into CO3 2-. In order for HCO3- to become CO3 2-, has it donated or accepted a hydrogen ion? Answer, donated. That makes hydrogen carbonate ion the acid, and the carbonate ion its conjugate base. Again, always two acid-base conjugate pairs in a given reaction. Let's take a look at hydroxide ion and think about what must happen in order for it to become water. Is it going to donate a hydrogen ion or accept a hydrogen ion? It's going to accept. And the Bronsted Lowry definition then tells us the hydroxide ion is acting as a base, and that water is going to be its conjugate acid. Again, think about this reaction in reverse. The water, which we have indicated as a conjugate acid, in fact acts as an acid in the reverse direction. It will donate its hydrogen ion to return to the hydroxide ion form. And the carbonate ion, which we've designated as a base, will in fact accept a hydrogen ion to return to the hydrogen carbonate ion form. All right, just some quick practice to refresh our memories on the Bronsted Lowry definition of acids and bases, and understanding and identifying conjugate acid-base pairs.